Welcome to today's webinar. The webinar is organized by the Indonesian Stainless Steel Development Association, in short INASSDA, and conducted by the International Molybdenum Association and the Nickel Institute. It covers the topic stainless steel's requirements for renewable energy. Today's presenter is Mr. Gary Coates, Technical Manager for the Nickel Institute in Toronto. Our panelist and organizer, Pak Johannes Kurniawan, General Manager of INASSDA. I'm your host today, Jörg Schweitzer, Manager Market Development in Southeast Asia. With this, I would like to wish you all a very interesting webinar, and over to you, Gary.
Thank you, Jörg, and thank you, Johannes. So today we're going to talk about stainless steels and renewable energy, and it's an interesting topic because a lot of things are developing now. They're changing, and so even not just changing from fossil fuel over to renewable energy, but even within the renewable energy field, there are new developments constantly taking place. What we're going to do as an overview today is talk about certain of the renewable energy areas: biofuels, geothermal, solar power, hydroelectric, wind, carbon capture, utilization and storage, and also how certain organizations such as INASSDA, the Nickel Institute, IMOA, and others can be of value. I'm not going to cover some of the other renewable energy technologies such as hydrogen, ocean currents, nuclear. Those are all relatively clean energy sources, but I won't have time to cover those in any detail at all. So a little bit on why stainless steel. Well, because stainless steels have many properties of value to the renewable energy production area. So first of all, there's a wide range of alloys suitable for a wide range of corrosion resistance, from just applications, maybe structural, that are resistant to atmospheric corrosion, to some very highly corrosive alloys for highly corrosive conditions. High temperatures. We can go up to about 1150 degrees C or slightly higher with these certain stainless steels. And we can go down to very low temperatures, liquid hydrogen temperatures, maybe even liquid helium temperatures if we had to with certain of the stainless steels. Strength, well, some of them have a moderate strength level and some of them have a much higher strength level. So we can fit the needs of the different strength levels for different applications. Life cycle cost effective. Stainless steels are not necessarily the least expensive choice, but they last over the long run, and therefore their life cycle cost can be very effective. They're durable and resilient in this time of climate change where we have floods and typhoons and all sorts of weather events that we have to be careful with. Stainless steels are durable and they last. They're resilient. They're earthquake resistant. They are so ductile. And sustainability, one of the key points, we all want to use materials that are sustainable. Stainless steel fits the bill. And one of the important points is that they're fully recyclable. At the end of life, you can make new stainless steel of equal quality to the old stainless steel, or even better quality than the old stainless steel by recycling them. Suitable standards exist internationally for all sorts of applications: structural, pressure vessel applications, food and beverage applications, not necessarily usable here, but there are standards available, and they are available in all sorts of product forms, the different alloys. So just a quick refresher on the families of stainless steel and the types, and we'll be mentioning some of these grades in this presentation. The austenitic alloys, the 300 series, 304L, 316L, 904L, 6-moly. Those are all 300 series alloys. They're commonly produced, the most commonly produced of all the families. They are highly ductile, reasonably strong, easily weldable, one of the most important keys for when we're trying to do fabrication, and they can be used from cryogenic to those very high temperatures. The ferritic alloys, for example, 430, 444, they're not commonly used in the chemical or petrochemical or renewable energy industry, but they do have some use in very specialized applications. The duplex alloys, which are a combination of the austenitic and ferritic structure, they have higher strength than the austenitic and ferritic alloys, and they have some special properties of interest. We'll talk about them as we go through the presentation. Wide range of family, and from the lean duplex, for example, the 2101, to the standard duplex 2205, to the super duplex 2507, and there's even hyper duplex alloys that are very specialized, very available only in the limited product forms, but it just shows you that you have a wide range of possibilities there. The martensitic alloys are one of the ones that are hardenable by a quench and temper heat treatment. Heat it up to a certain temperature, you quench it in oil, for example, and you can get a very hard and very strong material. Or the precipitation hardenable ones, which are hardenable by a different mechanism, a precipitation mechanism, where they're heated up to a certain temperature for a certain length of time so that the precipitates form, and then they don't need a quench after. And they have some special applications where you want to avoid distortion, which may come from that rapid quench of the martensitic types. And I'm also going to mention a little bit about nickel alloys. And nickel alloys are really a continuation of the austenitic series of materials. So they are, by definition, alloys that contain more nickel than iron. Of course, stainless steels are steels. They contain more iron than any other element. And this I'd like to show just to show that the different families have a wide range of corrosion resistance. I could also show the same for the strength, but some of them, such as the martensitic and pH grades, they only have sort of the bottom end of the corrosion resistance, starting with the 10.5% chromium, which is the definition of a stainless steel, up to a somewhat moderate level. Whereas the 300 series runs from a fairly low level to a very high level. And as I mentioned, those nickel alloys continue on into even higher corrosion resistance. The ferritic and duplex alloys fall into that same range roughly as the 300 series, but they do have other limitations. So let's have a quick look at what the International Energy Agency, which has a lot of very good publications on renewable energy, says. And if we look at their chart of the different renewable energy technologies on the left, and across the top, the different elements, alloying elements that are needed here. We have nickel and we have chromium, two important ones for stainless steel. The open circles mean that there's a low need in those particular applications. The gray is a moderate need and the dark is a high need. And you can see that for wind, for concentrated solar power, that's the CSP one. We'll talk a bit about that. There's some need for stainless steel, nickel, and chromium. Geothermal, there's a great need for that. Nuclear back to the gray, moderate level. And then in the International Energy Agency, they have battery storage. And of course, we all know that nickel is really important for batteries and also in the use in hydrogen here. Now, just to show that you've got to be careful what you read, bioenergy, they actually have an open circle for both chromium and nickel we see that bioenergy is existing now, one of the greatest users of stainless steel, and that'll be the first one that I talk about here. So biofuels, they're considered clean because the feedstocks for biofuels are usually plants take CO2 out of the air. And sometimes we're talking about the feedstock being a used cooking oil, going to the McDonald's and for your French fries, and the cooking oil, after a while they used to throw it away. Now most of it is being transformed into a biofuel or other types of animal fats. Of course, if biofuels are combusted, burnt, which is really their purpose, carbon is released back into the atmosphere. And since we use some carbon in the planting, the growing, the harvesting, and the processing, biofuels are not really carbon neutral, even if we can afterwards sequester the carbon. But they're an important part. We won't need liquid fuels. We want to drive cars and trucks that use petrol and diesel, and especially airplanes. You want a liquid fuel there, at least in the short term, because liquid fuels are easy to handle. You can replace existing liquid fuels often with little or no change to the engine. So let's talk about ethanol first. The major production today of ethanol from as a biofuel comes from either corn, sugarcane, or grains. It's a well-established, relatively simple technology, economically viable. The common stainless steels, 304L, 316L, are widely used, as well as some components in some special stainless steel and carbon steels. But about 95% of the plant is typically 304 or 316. Now, the United States and Brazil have been the major worldwide producers. In 2022, I saw it was about 80% come from those two countries, but other countries are embarking on a program to produce bioethanol. India, for example, has aggressive targets. They want to have 20% ethanol in all their petrol by 2025. That's, of course, only next year. They're about 12% now, but on average, and they probably won't make the 20% by 2025, but they'll come close. And that's something that we can emulate as a country, getting the ethanol into our petrol. So ethanol produced in this way from the corn, sugar cane, or grains contains a small amount of water, chlorides, and acid, and it results in a measurable corrosion of carbon steel, so stainless steel is needed. When I went and visited a bioethanol plant here in North America, I met the maintenance person there, and she said that her plant was basically 80% stainless steel, but she wished it was actually 100% stainless steel, because the only maintenance they do at that time was on the carbon steel, replacing it on a fairly regular basis. So it is good to try to optimize by using stainless steel 304, 316 in these plants. Now, when you take this bioethanol and blend it with petrol or gasoline, as we call it in North America, you can get stress corrosion cracking of carbon steel. So, of course, petrol, gasoline, you can normally handle with plain carbon steel, but when you blend it with ethanol, that water, chlorides, and acid in there can cause stress corrosion cracking of the carbon steels. And there has been a number of cases where the blending stations where they mix the ethanol with the petrol, you have experienced that. And of course, you don't want to have leaks of a very flammable fuel there. So those tanks and piping systems are most often stainless steel, again, 304L or 316L. Just as a comparison, other materials, aluminum, the E10 blend, which is only 10% ethanol, which has really been the common amount in North America anyhow. Aluminum severely corrodes. Brass components will corrode. The martensitic stainless steels, which have that minimum level of corrosion resistance, they have suffered pitting in some environments because the chloride content and small amounts of organic acid, acetic acid, is present. Certain plastics are suitable, but we have a real problem when other plastics that aren't suitable but are suitable for the petrol product are used, and then you put in the blended material, and then the plastic material leaches into the fuel and then gums up the engine. So you have to be very careful with using plastics. Now, we can take the carbon dioxide that is generated when we produce bioethanol. It's a relatively pure stream, easy to clean up, and although it has some uses, such as in food, it will also we can also use it to enhance oil recovery, and this is started to be done in the U.S. right now. A number of bioethanol plants have gotten together to capture and clean their CO2 and then send it in an existing pipeline back to the oil fields, pump it down, and that enhances the recovery of oil. And that's one way of also getting carbon out of the atmosphere. You're pumping it down. Otherwise, it's often just released to the atmosphere. Of course, there has been some objection to using agricultural products that can be used as food for fuel production. So there have been some major efforts to make ethanol out of waste agricultural products or waste forest products or other plant-based wastes. This is much more difficult, and one of the reasons is the large variability of feedstock requiring different treatment conditions. One feedstock might require a different pre-treatment process than another feedstock. This can make it very difficult. We need acid and high temperature, so we were looking at corn stover. That's the waste product from when you grow corn, and the higher the temperature, you use 1 or 2% sulfuric acid. The higher the temperature, the quicker the process happens. And so to make it really cost efficient, you do need a higher temperature there, and that involves highly alloyed stainless steel, perhaps the 6-moly stainless steels or 904L, or nickel alloys. The most effective use at the highest temperature was with the high molybdenum C-type alloys. But once you get beyond the pre-treatment stage, it's a relatively less corrosive process as the temperature drops. And so therefore the rest of the plant is normally done with the 304L, 316L type materials, or perhaps some use of duplex. Now, one of the things that I found confusing and confused me for a while is that there is a difference between biodiesel and renewable biodiesel. They sound like they should be the same, and biodiesel that you would make from oils and fats, your waste cooking oils, is actually different than what we make from produce renewable biodiesel, which can also come from those waste oils and fats, but are most commonly made from vegetable oil now. And I'm not an organic chemist, so I mean, I've been told that there are the differences. One is a fatty acid methyl ester, and the other is a hydrogenated compound. But there are a lot of small scale plants making just the biodiesel plant, biodiesel fuels, mostly from waste oils. But the major effort, at least in North America and Europe, has been making biodiesel from vegetable oils, so specially grown crops to produce renewable biodiesel. It's a cleaner fuel, runs more efficiently, and it can be made in the same kind of plant refinery that an oil refinery is. I'll come to that in a minute. But the sustainable aviation fuel is just really a modified kind of renewable biodiesel. And there's huge interest in with the aerospace industry. There's very little alternative to fueling aircraft other than some sort of renewable biodiesel. All the aircraft manufacturers, all the airlines want to reduce their carbon footprint, and they can do it through sustainable aviation fuel. So, as I mentioned, a refinery that can produce standard diesel can also can do the renewable biodiesel. And a lot of small refineries are now being converted in the US and Europe to use the vegetable oils. However, it may sound strange, but it was found out that these vegetable oils and fats are far more corrosive than most fossil fuels. Those of you from the petrochemical industry know about the total acid number. It's really an indication of the amount of acid in the oil, and that value is much higher for the vegetable oils. And it depends on the vegetable oil itself, how much the total acid number is. So rather than using chrome moly stainless steels or even carbon steels, which you can use in certain fossil fuel oil refineries, you need to start off at the front end with anywhere between 3.16 and 6% moly, depending on the type of vegetable oil that is going to be used as a feedstock. And of course, for a refinery, they have to consider, can we always get a particular type of vegetable oil, or must we design our plant to be able to handle different types of vegetable oil? So often they're going for the more conservative approach of a higher alloy material at the front end. There's a lot of research programs going on. I'm involved with one at the Materials Technology Institute where they're sponsoring some research to determine how corrosive these materials are. We'll also learn as these other plants start up. The next renewable energy source I will talk about is geothermal. Many of you are familiar with that. You use hot water or brines or steam from deep in the ground that are heated from the heat of the mantle of the earth, sorry, the heat of the core of the earth, rather. And you can extract the heat and use that to generate electricity, or use it for hot water for heating of buildings. And of course, in cold climates, that's a very important source of energy. You need to heat the buildings in the winter months. So typically where the heat for buildings comes is in the countries like Iceland or New Zealand. Essentially, you can get geothermal energy from anywhere, but really the ones we're talking about, the ones that generate the electricity, are mostly in the areas where they are close to volcanic activities. And there are different kinds of plants, geothermal plants. I won't go into details here, don't have time for that. One of the key factors is that unlike wind and solar, geothermal plants run 24 hours a day, 7 days a week. They supply energy constantly. You can turn them up and turn them down as you have a different energy demand. So they are very useful that way. They are a little more capital intensive. They cost a little bit more to build, the infrastructure to build, than solar and wind, but they have the advantage of being there all the time. And of course, Indonesia is a prime country for geothermal installations. There are some in Indonesia, I understand, but there could be a lot more. So the downhole condition, the local conditions vary immensely. Of course, everybody would love to use carbon steel, and many of the plants actually do. You can use the similar guidelines that you use for oil and gas production. The NACE MRO 175, ISO 15156 can also be used to help determine what is the appropriate material. Some of the other plants will use stainless steel, and there are even some that use nickel alloys. I'll mention one about that shortly. There are some cases we've seen where the casings will corrode after a while, and you reinforce them typically with a super duplex stainless steel alloy. The reason for that is the compatibility from a thermal expansion point of view, and you also get the high corrosion resistance. The top sides of the plants, well, it depends on the nature of the geothermal fluids as it goes into the first, the binary cycle plant, where you might have a heat exchanger, so you're not using that liquid to actually drive the turbine, of course. But all sorts of materials are used, ranging from the chrome, moly, vanadium, steels, not stainless steels for the rotors, to stainless steels of 12% chromium, the 17.4 pH, 316L, 2205 duplex, and 2507 super duplex, 6 moly, and even nickel alloys such as 625, which has 9% molybdenum in it. They are all used depending on the nature of the plant. So each plant will be slightly different. You must know the nature of the geothermal fluid. I'll mention the geothermal Salton Sea plant in California that has been operating now for about 20 years. And it involves very corrosive brines. They use the nickel-based sea alloys, which typically will have 12 to 16% molybdenum in it, and 625, depends on the actual temperatures involved. Also, the super duplex 2507 in a less aggressive conditions. But one of the reasons I mentioned this is because that brine also has some lithium, and they're currently adding a lithium extraction unit to one of the plants. Of course, we all know that lithium is needed for electric vehicle batteries, and so there is predicted to be a shortage of lithium, and it is always expensive to take it out, and there are some environmental considerations, but here the brine is already extracted. It's used in to drive the turbines and generate electricity. So they can use it, and by that time it's cooled down to a temperature where it is less corrosive, but you still need the high alloyed stainless steels. AMPP, and I'll mention about that shortly here, is developing a standard. We have been pushing them to develop a standard on materials for geothermal applications. There's a lot of knowledge that exists in the world coming from places where they have existing applications. But a lot of it is considered proprietary. We want a document that can be used as guidelines by anybody in the world to help them decide what materials to use. And finally, just last March, the AMPP had a group studying that, and they have decided to develop a standard on that. And in addition, they've had formal paper sessions and informational sessions. Nickel Institute has actually run the informational sessions for the last few years now on materials for geothermal applications. And in case you have not heard of AMPP, it used to be known as NACE. Most people are more familiar with the NACE name. I still use it, even though it's properly called AMPP today. And although the headquarters is in the US, there are 35,000 members around the world. I think 1/3 of them are outside of North America. And there is an Indonesian chapter of AMPP, and I provided the website address there if you want to have a look at it. There are conferences run in this area. There's one coming up in September in Singapore, and I know Indonesia will be well represented at that conference. Some of the energy technologies that do not use a lot of stainless steel, but still where stainless steel are important, are the photovoltaic solar systems. And solar PV and wind are the least expensive sources of renewable energy. The solar PV ranges from small installations on roofs of buildings to very large solar farms. There have been reports, insurance claims on a lot of solar installations that were damaged because of weather events, whether it was typhoons, in some cases it was floods, or that kind of weather activity has come in. And one of the areas we're looking at is the support frames. Traditionally, they're built of a lower cost material, either a galvanized steel, aluminum, weathering steel, but some are built in stainless. In Japan, they're using lean duplex. In Europe, for some roof installations, they're using 304 or 316 stainless, depending on whether they are inland or near the coast. But in these support systems, the fasteners are almost always stainless steel. So if it's a galvanized steel supporting frame, they'll use stainless steel fasteners. Same thing with aluminum, and same thing with weathering steel. And so stainless steel is important there for the fasteners. And as I say, it's a combination of better design and better materials will contribute to achieving a 25-year life on these solar photovoltaic applications. One of the new areas under development is the concentrating solar power. There are different technologies available. One of the more interesting ones is the tower system, where you have a series of mirrors that track the sun, and they focus the sunlight on a receiver at the top of a tower, and you can get some very high temperatures there, 500 to 1,000 degrees C. And of course, with the higher temperatures, you can get higher power efficiencies out of the electrical generators. You can store the heat as a molten salt. Usually we will use molten salt in running from that receiver down to the generator. The molten salt can be stored for when the sun is not shining, but the power is needed, or in the evening when the sun is low on the horizon. So there's a lot of interest in this technology. The receiver materials are typically a nickel alloy, the 625 with 9% molybdenum is the standard grades. They can use sometimes a lower alloy material, the 800, which is actually classified as a stainless steel in the North American classification, although we think of it often as a nickel alloy or alloy 230, which is a true nickel alloy. Heat storage tanks for molten salt can be 347H, and they will typically use the structural stainless steels 304L 316 as support structures. These are moving structures, so you want to be able to have high fatigue life in a somewhat corrosive environment. And right now, the U.S. Department of Energy has a program to design and test. It's been built now, one where steam temperatures up to 700 degrees C will be, occur in the steam, and it'll be like the advanced ultra supercritical coal-fired power plants. And there they need special nickel alloys. 740H, 282 are new alloys that are being tested out for that application. So I'm going to just talk briefly about hydroelectric. That's certainly not a new technology. They use a relatively small amount of stainless steel, but the key components, again, will need to be a stainless steel due to the erosion coming from water at high velocity. Cavitation, that's where actually a little piece of the material pops off because of a very high velocity or corrosion issues. Water is corrosive to a certain extent. The turbines are often made of a martensitic stainless steel, usually with a nickel addition, which helps in the weldability or repair. So a grade called 410 nickel moly, or the cast equivalent is Ca6Nm, or similar alloys are used. The company I used to work for had a martensitic ferritic austenitic alloy, a triplex, if you want to use a name for that, which was a weldable grade that was used in Francis turbines. So there are different technologies for turning water, pressure of water into electricity. And depending on the turbine type, there are different preferences. But things like the penstocks, that's the pipe that brings the water down from the, let's say, the dam to the turbine. They are often now being made in stainless steel so that they don't have to be replaced during the lifetime of the installation. And even the dam gate components are often made using stainless steel, again, for long life. Here's where that 17.4 pH, which doesn't require a quench afterwards and therefore low distortion, is used for certain components where where you have long lengths. They might be 50, 70 meters in length, and you want them perfectly flat, and the rollers of the dam gate will go against it. And you want low maintenance in those applications. There is wind in power generation. We talked about it, and of course, wind can be turbines can be either onshore or offshore. The difficulty with wind turbines is wind is intermittent and somewhat unpredictable in supply. There are some videos on YouTube that show people trying to get to these offshore wind turbines, both get into the towers and to also even do the substructure underneath the water. They are very difficult and therefore very expensive to maintain. So there are a lot of challenges with them today. And there will be in the future too. But so the people are looking at trying to have low maintenance wind turbines. Doesn't matter whether it's offshore or onshore. Now, most of the wind turbines today are in the area of 3 megawatts, but they want to go to higher power capacities for an individual installation. And maybe even going up as high as 17, and people in China are talking about 20 megawatts. So the that means that you need very, very high towers, just with longer blades, and the heavier nacelle, that's the part at the top that generates the electricity. So this picture is actually of a relatively small wind turbine tower. You can see they're quite big. They're made of very thick material. For the most part, stainless steel is only used in safety-related components, ladders, fasteners, electrical boxes, things like that. And of course, we have to remember that the offshore turbines are in a more corrosive environment with the silt from the sea splashing, or the mist coming on it. So they tend to be very corrosive environments. Still, you don't want to use stainless steel for the towers themselves. That would be very, very expensive. However, the carbon steel that is used, you see thicknesses up to 125 millimeter and more. You need very high fatigue strength, and you think of these offshore ones bobbing around in the ocean. And especially the heat affected zone of the weld is where the critical fatigue property is needed. There are only a few plate mills in the world that can make plates in the required thicknesses. You want wide plates with less welding and longer length, so you can get longer, you can do the whole diameter in one length of pipe. So very heavy plates. And though this isn't stainless steel, the Nickel Institute has a project underway with right now 2 European plate mills to improve the properties of the material by using a small amount of nickel alloying. And here we're talking maybe 0.75% nickel. So it's not a stainless steel by any stretch of the imagination, but the little bit of nickel helps a lot in the fatigue properties, the toughness, which is really toughness. The opposite of toughness is brittleness, so it helps in cold weather. We have some wind turbine towers in northern Canada where it can be minus 50, minus 60 degrees C in the wintertime there, so toughness is extremely important for them. The final technology I'll talk about is not really renewable energy, but it relates to reducing the carbon footprint of some applications that are using fossil fuel, but also ones that are using, for example, biofuels. There are 4 distinct categories of carbon capture, utilization, and storage. One is where you have an existing process and you modify it. Or you actually do an add-on unit to an existing unit to clean up and concentrate the exhaust gas, so you take out the CO2, and then you either can use it or store it underground. There are systems to transport the gas, including the permanent storage or transport it for later use. Systems that actually try to use the CO2 gas to make some useful product from it. And then there are, the final one is the direct capture. Air contains only about 0.041% CO2. So that technology, people are working on it, but tends to be very expensive. We'll talk about each one of those ones. The picture on the left is of a power at a coal-fired power plant. It's in Canada, where I am from. And so it's an existing coal-fired power plant, and they've added on a system that will remove the CO2. And I think, yeah, there it is. The text on that. You first have to take out the sulfur dioxide from the flue gas, so that involves alloyed stainless steels. You need to take out the particulate and some of the other impurities, and then you remove the CO2 in the same way that a refinery removes CO2 from its process streams, natural gas streams, for example, using a solvent. And so the process is not particularly cost effective. It is expensive to do that, but allows you to continue using an existing coal-fired power plant. In that particular case, the CO2 is then sent, in this particular case, across the border to the United States and is used for that enhanced oil recovery. An example of where you modify a process to concentrate the CO2 better is where you can use natural gas and you burn it in a special way that creates a high purity CO2 from it. And one of those is the alum fitted Franco. There's, I believe, 3 plants operating, or 2 plants operating and 1 under construction now, where this is being tried and tested. It's a proprietary information on it, but we know that nickel alloys and stainless steels are necessary there because of the high temperature sections. Transporting CO2, well, I mean, we think most of us will realize that when carbon dioxide is completely dry, it's non-corrosive to carbon steel. You can handle and transport in carbon steel. When it's dry and you compress it or liquefy it, carbon steel is still suitable, but because of the lower temperature, you want a higher toughness material. So we add a little bit of nickel for that, but you also add a little bit of nickel to the carbon steel to give it a higher strength, because when it's compressed, you have a pressure there. So you want to use a higher strength steel. Those again are not stainless steels, but they're carbon steels that are optimized to give the higher strength, but the low temperature toughness. And of course, when CO2 gas is humid, you get an acidic liquid, carbonic acid, and that is corrosive to carbon steel, and therefore you need stainless steel. Some people will do a coating on carbon steel, but coatings tend to not last the expected lifetime of the components. Here, that AMPP organization has already come out with a guide. It was written by DNV in Norway, actually, of material selection and corrosion control for carbon dioxide transport and injection. A very, very valuable document and highly recommended. If you are a AMPP member, you can download that document for free. That guide just came out a couple of years ago, and it's very, very I've found it very, very useful. There's a lot of development work going on in trying to use the CO2 gas rather than trying to store it underground, try to use it for applications. Already we use it in agriculture for making urea fertilizer, or making ammonia and then urea fertilizer, in food production and welding gases and a lot of other smaller uses. But there is a lot more CO2 available, or there will be, than what people can use now. Of course, the enhanced oil recovery is the greatest use of recovered CO2 today, but people are working on production of fuels and fertilizers, chemicals, building materials that will use the CO2 and tie it up, store it in a permanent or semi-permanent fashion. And all those technologies will be using nickel-containing stainless steels, and some cases nickel alloys, the low alloy nickel-containing steels, and even nickel catalysts are needed there. So there's a lot of development work, a lot of work at universities. Perhaps some of the universities in Indonesia are working on some of those systems too. And finally, I mentioned about direct capture. It's very, very expensive. Some of the mines up in Canada, nickel mines and diamond mines, and some of the other ones around the world They have magnesium-containing rock as a waste material, and that rock will naturally absorb the carbon dioxide, producing a solid magnesium carbonate, which can be stored permanently, easily. It's a very slow process today, so the quest is to speed up that process. And so many of the nickel mines are undertaking to do this so they can lower their carbon footprint and offer a low carbon nickel to the world. A lot of the battery manufacturers would like to say the nickel we have comes from a low carbon footprint material. So in summary, there's a lot of exciting opportunity for stainless steel and renewable energy. I'm excited about it. I see all the developments. It's hard actually to keep up to date with all the technologies that are being developed. And a lot of them, it's a little bit unclear what materials are needed. I was one as an independent consultant involved in one using waste forest products and whether it works, whether it'll be economical, that remains to be seen, but it will start up later this year. I find it very exciting, and I hope you do also. And there is a need to ensure that all these plants are built to last. Selecting an inferior, less expensive material that requires either constant maintenance or results in failure and results in huge new capital costs, that really doesn't make economic or environmental sense. So it's really important to ensure that when we select a material for the particular application, that it is the right material that will last the expected length of time on the equipment.
Thank you very much, Gary. Dear listeners, if you have any questions concerning this presentation or about any nickel-related topic, kindly send us your question via our webpage. Once you enter www.nickelinstitute.org, you will immediately see the yellow banner Technical Help. Click on it, register, it's free of charge, and fill in your question. One of our experts will come back to you fastest. Thank you all for attending this webinar. We are looking forward to have you on one of our next webinars again. Goodbye.